So we can start right now. I will add your presentation to the screen, okay? And I will leave you alone. So after your presentation, again, we will have a Q&A session. We'll discuss some points there, okay? So good luck and rock the stage then.
Thank you, Pavel. So hello everyone again. It was really nice to to have this free facts icebreaker. And now it's time for my talk, which is titled, Where is my cache? Architectural Patterns for Caching Microservices. In this talk, I will focus on how you can do caching in your system and give some pros and cons of each solution. But first, a few words about myself. So I'm an integration team lead at Hazelcast. I used to work at Google and CERN before. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings. But on a daily basis, I do coding, I do technical stuff. A few words about Hazelcast. So Hazelcast is a distributed company, and it is distributed in two meanings. First meaning is we produce distributed software. Our products are Hazelcast, Hazelcast Jet, and Hazelcast Cloud. And the second meaning is that we always worked remotely. So it's a distributed company. We are located all over the world, and the company was founded as a remote company. We write open source software, so you can use most of our stuff for free. And you can also contribute and send us a PR. That is the agenda for the talk. So it is pretty simple. There will be a short introduction about caching in Microservice World, and then we'll walk through all possible caching topologies that you can use in your system. And while I'll be talking, I would like you to think about two things. First thing is, which of this pattern do you use in your system? Because you most probably use caching in your system, and you must use one of this pattern because this list is complete. And the second thing I would like you to think about is, would it make sense for my system to change to any other pattern? Would it make sense to change the topology of my caching? And with the questions, I would like to start the talk. So that is the classic microservice world. So we have a lot of services, they use each other, they are written in different programming languages, they can have different versions. So generally, it quickly becomes very complex as the architecture. Now the question for this talk, where is the right place to put your cache? Is it inside of each service? Or maybe outside as a separate unit in our architecture? Or maybe you should put cache in front of each service. And that is what this talk will be about. So the first pattern you can use, the first topology, is embedded cache. Embedded cache is the simplest caching you can imagine. You put cache as a library inside your application. The flow looks as follows. So there's a request going to our system. We usually have a load balancer, which load balances the traffic, and it forwards the request to one of the application replicas. And now each application has as a library a caching. And now it checks, okay, if I already processed such a request, if yes, take the value from the cache. If no, do some business logic, put the value into the cache, and return the result. So the logic is super simple. It's so simple that we could even think about implementing this on our own. Like if you happen to use Java, that could be your implementation. So you use some collection like concurrent hash map. Now check if the request is in the cache. If yes, return the cached value. If no, do some processing, put the value into the cache and return the response. So you can implement it on your own. However, please don't do it. Don't do it because a collection is not good as a cache. Because it has no eviction policy, no max size limit, no statistics, no built-in cache loaders, no expiration time, no notification mechanism. So a simple collection in any language is not good enough as a caching library. So we need something better. And this something better, if you happen again to use Java, for example, there is a Guava, which is a very good library where you can define all these features upfront while constructing your cache. Another good library for Java is EHCache. If you don't use Java but some other programming languages, then you will find your caching library. For every language, there is a good caching library. Now, we can even take this idea of caching and take it one level higher and put the caching into our framework layer. Like if you use Spring in Java with Java, then to apply caching to your application, it's enough to mark your method cacheable. And now each call to this method will first check, okay, have I already executed such ISBN? If yes, return the cached value. Only if the value is not found in the cache, then execute a method find book in slow source. However, be careful because for some reason, Spring uses concurrent hash map by default. So you are better off changing your cache manager to some real caching library. So this is the first thing you can do with your Spring application. Now, embedded cache is super simple. As you've seen, like you can use it with Spring, with whatever framework, you can even use it without anything. However, there's one problem. Imagine that a request goes to load balancer, it is forwarded to the application at the top. We make some long-lasting computation, put the value into the cache, return the result. Now, the same request can go to our system, but it can be load balanced to the application at the bottom. And now we have to do again the same business logic because these caches, they are completely separate. There is no, they are different things. So one of the improvement to our embedded cache is to make this cache distributed. So embedded distributed caching is not a separate pattern because it's still the same idea. However, we will just use a different caching library, which is a distributed cache. So this time we'll use Hazelcast. Hazelcast is a distributed cache. So now the flow is exactly the same. However, both caches in both application replicas, they form one consistent caching cluster. And Hazelcast is just a library. So if we stick to this example with Spring, all you have to change is your cache manager and say, okay, I would like to use Hazelcast as a cache manager instead of this default concurrent hash map. So let's look at a quick demo how it looks like in practice. So in my project, I have a very, very simple, like a service, which this is exactly what you've seen on the slides. It takes the book and searches for the book. To simulate like long-lasting business logic, I sleep for 3 seconds. And now my whole cache configuration for this is, okay, asking Spring to use Hazelcast Cache Manager. That's all. There's nothing more I implemented. If we start our application, which is a standard Spring application, first thing you will see, it takes some time to start because it's, after all, it's Java with Spring, so it takes some time. But we will see that it started, this log means it started Hazelcast member, one Hazelcast node. If we start this application, the same application again, they should find themselves and form one consistent caching cluster. So now, no matter which application replica we use, we will put the value into the same cache cluster. So 1 second more, and then we should see they formed one consistent caching cluster. And this log means, okay, they found each other, these members, and they formed one caching cluster. Now, a question you might ask is, how is possible that these two Hazelcast members, they just found themselves. And we thought how to implement it. I've run it on my laptop right now. So they used multicast by default and they found themselves. That was an easy thing. However, we thought how to make it like production ready so that it would be super simple for the users to form a distributed cluster. And we came with the idea of discovery plugins. So we implemented a lot of plugins for each environment. And now Hazelcast detects, okay, I'm running in AWS, so I use AWS plugin and use AWS API to find other members. So from the user's perspective, it's super smooth. You just run your Hazelcast wherever you want, and it finds the environment and it finds other members. If there is no plugin for your environment, then you can either implement it on your own or piggyback on Uroka or Zookeeper for the service discovery. If you're interested in details, we publish a lot of blog posts on how to configure this on Kubernetes or how to set it up with Eureka or the AWS, etc. So we ended up with the diagram like this. So a short summary for embedded and embedded distributed caching. What was good about it? So the configuration was super simple because the application went together with the cache. We have very low latency data access because the cache is together with your application. And usually there is no separate ops team needed or DevOps effort needed. From the downside, your cache is the management of the cache is not flexible because if you would like to scale up your caching cluster, you need to do it together with your application replicas. It's also limited to JVM-based application or whatever is your language of choice. And the data is collocated with application, which may or may not be a problem. It depends on usually on your enterprise. What we've seen, like our customers, if they are big enterprise customers, they never want to do embedded caching. They always do client server. So the next pattern is it's client server. So client server is kind of a database style. It means that we set up our caching server separately, and then application connects to the server and use it. So if we compare this diagram to this embedded cache diagram, there are two main differences. So the first difference is we have this thing on the diagram. So this thing is a cache server and it needs some management. So we need to do some scaling. We need to think about security, etc. Usually what we see is like in big enterprises, there's a separate dedicated team just to manage not only cache, but also database, etc. So they manage it's the server part. But if we compare this diagram also to embedded mode, there's also a second difference. This is this part. Now the application uses cache client to connect to cache server. And what it means for us, that means that we can use a different programming language in the application and different for the cache server. And that is a very common strategy, that you have a lot of that you have cache servers and your microservices are written in different programming languages, but they all can connect to the cache server because there's a well-defined protocol between the server and the client application. This client server is so common that a lot of tools, they support only this. Like if you look at the Redis is, I guess, written in C, so you cannot easily embed it into your application. So they only support like client server. The same with Memcached. So it is a very, very common practice. How to configure Hazelcast as a server? So if you would like to just start a server, you can use a CLI, Hazelcast start, and it will start Hazelcast server. If you run in Kubernetes, we provide a Helm chart, also an operator, so you can, with the Helm chart, you can just install Hazelcast and it will spin up the whole Hazelcast cluster together with our management center monitoring application. How to configure the client? So for the client, there is no difference in the configuration. It will find out that you are running in Kubernetes, and it will discover your server automatically. So coming back to this diagram, so we usually, as I told you, it's like in big enterprises, this management part is provided by a separate team. So we can even move one step further and put this server part into the cloud. So again, the cloud is not, in terms of the architecture, not so much different than client server, but it's such a specific thing because the server part is not managed inside your organization. So it's again like database style. It's again, application uses some client, but this time you don't need to do all this management stuff. You don't need ops team. Instead you pay for the cloud provider. How does the configuration look like? So if we stick to this to the Spring example, you define a cache. So you set up your cache server in the cloud, take your discovery token, put it into your client configuration, and that's it. And it will automatically find your server. A quick demo on how to set up your Hazelcast cloud server. So if I go to the cloud hazelcast.com, you need to sign up and log in to your console, and then you have a web console. We also have a CLI for this, but if we use web console, then you create a new cluster. We can create a cluster. We set up the underlying cloud provider because we don't provide the infrastructure. We use some cloud providers as the underlying infrastructure. You select the region, the size of your caching cluster, version, how much memory do you need auto-scaling, and all these parameters, and create cluster. Now, while the cluster is being spin up, I would like to stress out a few things. So in the caching, the caching domain is very low latency domain, and the requirements are even more strict than for the databases. That is why that if you set up your cache server in the cloud, you better make sure that you set up in the same region where your application is located. But that is not all. You should also make a VPC peering. We provide an ability to peer your VPC when your application is running, for example, in AWS, with the cluster we created for you, so that they are in the same network. And it is very important because even one router hop for the caching is a lot in terms of the latency. So we have our cluster running. You can download for different clients the configuration, or we can take our discovery token and put it into our Spring application. So it will be exactly the same application we've seen, but in the cache configuration, we need to specify our discovery token and the cluster name. Now, if I run this application, we should see that using this discovery token, it should find the caching cluster spin up in the cloud and connect into it. Obviously, I'm now located in. Okay, we can see that this was this cluster in the cloud. Obviously, now I'm located in Krakow in Poland. I've spun up this cluster in, where was it, in US. So this is not a good example because latency is super high, but you get the idea. My application should be running on AWS, on this region, North Virginia, and I should provide the VPC peering so that technically my application and the caching cluster are in the same network. Coming back to our presentation. So here are the pros and cons of client-server cloud caching. So from the good side, data is separated from the applications, which is usually a must for big enterprises. We have a separate management, so we can scale up, down cluster, not touching the application layer. And it's programming language agnostic because there is a well-defined protocol between the client application and the server. From the downsides, we need to have some separate ops effort or pay for the cloud. The latency is higher, and we have to think about it. I mean, it's not always higher, but we have to really think about latency. So I already described the cloud part, but if you set up your own on-premises server, then make sure it's in the same local network than where your application is running in. And that is super important. Okay, we covered client server. So the next on our agenda is Sidecar. So you may say, like, this client server embedded, these are very old concepts. Sidecar is something completely new. Sidecar is something that is dedicated for the containers. That is why this diagram is Kubernetes specific. So a short introduction to the Kubernetes. So in Kubernetes, a deployment unit is called a pod. And this pod usually contains one container with your application. Now, you can put an additional container in the same pod. And this additional container is called a sidecar container. And it usually does some additional job, like redirecting your logs somewhere. This can be a good example for a sidecar container. The important thing is that your application and the application container and sidecar container, they are always deployed on the same physical machine. So with this introduction, we can simply put our cache server as a sidecar container and deploy it together with the application. And now the flow will look as follows. Request goes to Kubernetes service, which is a kind of load balancer in the Kubernetes world. This request is forwarded to one of Kubernetes pod, and inside the pod is the application that takes the request. It uses cache client to connect to the cache server, which is always located on localhost. It's always on the same machine because it's just deployed together as a sidecar. And obviously, there's all these cache containers, they form one consistent caching cluster. So this solution, the sidecar, is kind of somewhere in between embedded and client server. It's similar to embedded because we run the cache on the same physical machine as the application, and it scales up and down together with your application, and there's no discovery needed. It's always localhost. So, but it's also similar to client server because after all, we use cache client, so you can use any programming language, and cache server and cache application they are run in separate containers, but in the same pod. So there is some isolation between them. How it looks like in practice. So if we stick to this Spring example, so what you have to configure is a static configuration with localhost to your cache server. But this looks static, but in fact, the whole system is dynamic. We just know that your cache server will always be available at localhost. This is the Kubernetes configuration for this. So we have our application, which is our business logic, and we have a second container running in the same pod, which is our cache server. Short pros and cons of the sidecar caching. Good sides is configuration is very simple, and it's programming language agnostic. We also have low latency because cache is close to your application. And there is some kind of isolation of data between your application and the cache. From the downsides, it's limited to container-based environment. Sidecar is not only in Kubernetes, but it's always in the container environments. The management is still, again, not flexible because we scale up, down caching cluster together with the application. And after all, the data is collocated in the same application pod. The last caching pattern we'll cover today is reverse proxy caching. So reverse proxy caching is something completely different. It's completely different because so far in all our examples, in all our patterns, the application was aware that such a thing as a cache exists. Now we'll make it different. Now we will put the cache in front of the application, so application will not even know that such thing as a caching exists. So this is our diagram. The flow is as follows. Request goes to our system. It goes to the load balancer. And now just before or just after load balancer or together with load balancer, we have a caching. And now if the value is found in the cache, it's just returned. Only if we don't find value in the cache, it's forwarded to one of application replicas. So you see, application does not even know that there is a caching. If you would like to implement something like this, NGINX is a very good solution because NGINX supports caching. That is all you need to add to your NGINX configuration to add the caching layer. NGINX is good, but it has some drawbacks, like it is only for HTTP, it's not distributed, it's not highly available, and data can be stored on the disk. NGINX offloads the data to the disk. It's like slightly different, like Hazelcast is only in memory, so you can trust that the data access is fast. Here you have to think about it. You can find like some modules for NGINX which will provide this functionality. For Hazelcast, we don't actually have yet the module. For Redis, it exists. It's not very mature, but you can use it so that NGINX with Redis module. One last variation of the reverse proxy caching would be combining this with the sidecar and do reverse proxy sidecar caching. Again, with the sidecar, we will limit ourselves to the Kubernetes. So the flow now is as follows. Request goes to Kubernetes service, which load balances the traffic to one of the Kubernetes pod. But now inside the pod, it's not the application that receives the request, but it's reverse proxy cache container. And only if the value is not found in the reverse proxy cache container, then the request is forwarded to the application container. So, with all this, if we look at this diagram, in general, like about reverse proxy caching, and the application not being aware of the cache, this approach has some good and bad sides. And let's comment on this a little bit and start from the good sides. So what is good about it? Like why we would like application not to be aware of the caching? You probably remember this diagram from it was one of the first slides of this presentation. So we have a classic like microservice system. A lot of services in different versions, written in different programming languages, they use each other and so on. Now, if we look at such a system, we can do some performance measurement, and we can, using reverse proxy caching, we can say, I would like to add caching to this service and this service, and you don't even need to touch the code of the service. So it's in a declarative manner, in a configuration way. You just change the configuration and you add the caching functionality. And that is the whole beauty of reverse proxy caching, that you don't touch the code of the service. That would be if we would like to implement it, that is how it would look like. So we did a POC, like a prototype of reverse proxy caching in Hazelcast. And this is how you would need to configure this. So starting from the bottom, we have our application service. Then we need to have caching proxy is this service cache, this interceptor of the request. And we also need to init container, which will change how the request goes. because normally in the pod is the application that will receive the request. We need to change the IP tables so that it is the reverse proxy caching container. So we change the IP tables so that each request which goes to our pod from outside the pod, on the port 80, it goes to the reverse proxy cache container, but from inside on the same port, we go to the application container. That is all our init container needs to do inside our pod. Now, for this reverse proxy sidecar, there is actually no major solution yet. We did a prototype in Hazelcast, but it's nothing you can use on production. But Istio recently implemented the caching layer, so it's delivered together in an Envoy. So if you plan to use Istio, that is the way you could soon do caching. But this whole idea that the application is not aware of caching, it also has some bad sides, like the drawbacks. If you detach your caching from the application, there is one thing that becomes more difficult. And if you look anywhere on the internet, what is the biggest problem in caching? Everyone will tell you the same, that it's cache invalidation. Meaning, when to decide that your cached value is stale, that you should not use it anymore, that you should go to your service and recalculate it. And if the application is not aware of the caching, then if the application is aware of the caching, then you can use some business logic, like say, okay, I would like to remove this cached value if something happens. However, if your application is not aware of the caching, then you are basically stick to some HTTP, ETAX, timeout, basically timeouts for the cache. And that is the biggest problem actually with this reverse proxy caching. A short summary on the reverse proxy and reverse proxy sidecar caching. Good sides and the reason why you will use it is only configuration based. So you don't need to change our application. So it's obviously programming language agnostic. It's everything agnostic because it does not even touch your application. And it is very consistent with the container world, how it looks like, all this Istio movement. So I strongly believe that will be the way you will do caching soon. From the downsides, it's more difficult to do cache invalidation. There's no major solution yet for the sidecar version, and it's protocol based. And this way we covered all the caching patterns. As a short summary, I will try not to repeat anything I've said before because that could be boring for you. So what I proposed for the short summary of this talk is a quick decision tree which can help you decide which caching topology is for you. So the first question I would ask is, does my application need to be aware of the cache? If no, do I run containers? If no, use reverse proxy like NGINX. If yes, use reverse proxy sidecar as soon as there is a major solution available. However, if your application needs to be aware of the caching, then the next question you should ask is, do I have a lot of data? Or do I have some security restriction, like working in a big enterprise? If no, then if you are language agnostic, if you don't use containers, use embedded cache. If yes, use sidecar caching. However, if you have a lot of data working in a big enterprise, the last question you need to ask, is my deployment a cloud? If no, use on-premises server. If yes, use cloud cache. That is my maybe oversimplified decision tree on how to choose the right caching for you. And as the last slide for this presentation, I would like to share the resources. So the first one is the GitHub, where you can find all this demo I've seen and even more, all the caching patterns, how it looks like in the code. Second one is the blog post on how to set up Hazelcast as a sidecar container. Third one is our prototype to do reverse proxy sidecar caching. And the last one is a very good video talk about NGINX, using NGINX as a reverse proxy caching. And with this last slide, I would like to thank you for listening. It was super nice to speak to you. And do we have any questions?
Yeah, thank you very much. So many helpful resources. It was really informative, and so many use cases. You covered strategies, how to choose. Yeah, that was really nice. Decision tree was good. It was great. Thank you very much. Yeah, right now we have a Q&A session, and there is a couple of questions from we have in the chat. So the first one: how can I know if I need a cache or not? I think.
So if you need a cache or not, it will. I mean, if you don't need cache, good for you, because caching have a lot of problems. But usually, like, the cache is to improve the resilience or the performance. These are the two reasons why you use caching. So first is the performance. So you don't want to do some long-lasting computation more than once, so you do cache it. So you look at your system, do some performance measurement. Okay, I need caching. And the second is resilience. So you can think about it like one of your services may be down, but you can still provide a cached value, and sometimes it's good enough. Like a good example can be like Amazon recommendation service, where you may see recommendation and it can be a cached value, but you don't see that the recommendation service is down, because as a user you don't even notice this. So basically, performance and resilience, and these are the reasons.
Okay, yeah, true. Okay, so the next question is, what are the performance latency difference between different caching patterns?
Yeah, so the latency, like obviously the best latency you can get is where you have non-distributed embedded cache, because then it is at the process level. It does not even use network. Now, the rest of the patterns, in terms of latency, it will depend on your network configuration. So this is what I meant in this. When you set up your cloud cache, you have to think about your VPC peering, the same region. If you set up your cache server, then you have to think about where your cache server is located. It should be in the same local network. So I would say, like, normally if you use embedded cache, you have to think less about it, because usually your application replica will be already in the same local network. But you can get the same latency with in any distributed cache, no matter of the pattern used. You can, if you have good network configuration, you will get the same latency.
I see. Okay. I hope that we covered this question fully. And the last one, like about the encryption, do we need encryption in this caching layer or not? Do we have any kind of practices there?
Yeah, so that will depend, because like if you use something that I just show, one of my demo in the presentation was set up the cluster in the cloud and use it from my laptop, then obviously you need encryption, because otherwise someone else can just join your cluster. However, if you used, for example, your cache server and cache client in the same closed network, so then you don't actually need encryption, because you are safe, like you are firewalled from the world. So then you don't need it. And we see a lot of people doing this because there is always some overhead because of the encryption. And again, caching is something you use really, you would like to have really low latency. Yeah. That is why sometimes you have it in the same network and where your application is, but you don't allow access from the outside, and then you don't need encryption.
Yeah. and there is like a problem of the programming, like 3 problems, like naming, and one of the problems were like invalidating of the cache, right?
Yes, it's everywhere. Everyone struggles with that, and there is no good solution how to invalidate it.
Yeah, that's true. Okay, basically that's it. We covered all the questions, so we answered all the questions. Yeah, I'm very happy that we have your presentation, and that you covered so many things, and it was really interesting for me as well to listen. Basically, I'm a mobile developer, but it was very clear and very helpful for me to listen about those use cases and solutions and everything, all the layers. It was interesting. Thank you very much.
Thank you very much.
Yeah. Like right now, yeah, basically that's it. That's all what we have today. Like we will send you the feedback form later after the meetup, maybe tomorrow. Tomorrow we will send it, and we will share it with you. So, and right now, yeah, thank you very much everyone who was with us, who was listening to us, who were there, and let's see it in the next year. Yeah, it was the final countdown for this year, for the final meetup this year. So yeah, happy holidays, and see you in the next year. Thank you.
Thank you. Bye bye.